All right, Pre-Calc, it's time to get started into our first chapter, first book, first section here. If you remember in class, I told you that first chapter's name is Prerequisites, and that's why it's chapter P, and we're in our first section here tonight. So we have P.1, algebraic expressions, mathematical models, and real numbers. And what's important to remember here is some of this is review. Some of it, though, is setting the tone for the format and the way you need to write things as far as your answers, as far as what's true and what's not true. So it is important that some of this, even though it is review, you kind of take the time to look at the details because it will affect things down the road in pre-calc. So a quick reminder, algebraic and expression you've been doing since probably like third or fourth grade. Combination of variables and numbers using the order of operations with addition, subtraction, multiplication, division, as well as powers or roots. So we're going to start out right away with the order of operations agreement. And I have this note here, and it's good to read through it, but just a quick reminder, we're really talking about your please excuse my dear Aunt Sally for our order of operations. Now, in a few details here, the P stands for parentheses, and what's important is always start with the innermost parentheses and work outward. But the second part of this rule is what I really want to focus on because this is what we sometimes forget. If an algebraic expression involves a fraction, the numerator is its own parenthesis. It's invisible, but it is under a parenthesis. The denominator is one big parenthesis, again invisible, but both of those need to get down to one number or one value or the most simplified expression before you can work with the fraction as a whole. Now, fractions aren't the only thing that have those invisible parentheses. Another one would be your absolute values. Okay, if you think about it, when you see absolute value bars, you need to make sure what's inside gets down to the very, very simplified value before you try to take the absolute value or work with the absolute value. And the other one I want to point out is radicals. If you have a square root, a cubed root, or so on, if there are numbers or values inside underneath that, you really need to do everything you can to simplify those values first before you try to take and work with that radical. So parentheses, some are invisible, some are not. Make sure we are watchful for those. Our E, and please excuse my dear Aunt Sally, stands for evaluate all exponents. Okay, so if we see any exponents, do what we can to simplify those before we move on. M and D, I did not make a mistake when I wrote them together. They do go together. They should not be separated. And this is our multiplication and division, and what's super important as they occur working from left to right. So it is okay to divide first if it appears first in your number sentence. And the same goes for addition and subtraction. Again, they're together, they're linked, and they don't have to be addition then subtraction. It is what appears first from left to right. So make sure you're aware of that. That is one that we sometimes forget that rule after a while, so you do want to make sure you're careful on that. So our first example say evaluate the expressions. Just a quick reminder because sometimes it's such a small word, but if we don't remember the exact meaning of it, it's going to make us mess up. Evaluate is a synonym for simplify. And the reason we put evaluate and not solve is there's no equal signs in my expressions. Expression is just a combination of variables and numbers with some operations on them. There's no equal sign there. So if you look at number one here, here is my expression. It uses some variables, subtraction sign. There's no equal sign here. So that's important to know. That's why we simplify it. We don't solve it. Okay. So on number one, they give us this expression, and then they give us some values for x and y. So let's do some plugging and chugging here. So 8, I'm plugging in the negative 3 for x. Let's do the cube and minus 2. Okay, so the first thing we have here is I'm looking for parentheses. I do have parentheses, but these are not parentheses that have grouped things together. This is simply to hold that negative on with the 3. So it's just a holding parentheses. That's all this is doing. So I don't need to worry about parentheses. Move on to exponents. I do have an exponent of that third power. So I have negative 3 to the third power. Remember, that means whatever is to the third power means times itself 3 times. So negative 3 times negative 3 times negative 3. And that will make a negative, since there's 3 of them, and 27. Again, I still see those parentheses, but still they're just holding that negative on there. And it's important to know that because those parentheses are also right beside a number, that stands for multiplication. So I'm done with parentheses, done with exponents. I'm now going to multiply or divide from left to right. My first one that I see coming from left to right, just like I read, is multiplication. So 8 times negative 27. By the way, if we take a quiz or test on this, I'm probably going to say no calculator. So wouldn't be bad to practice with no calculator too. 8 times 7 is 56, carry the 5. 8 times 2 is 16, add that carried 5, and we get 21. And if I had a positive and a negative multiplied together, I have a negative. What's the chance you can read my writing right here? And I still have minus 2. Done with parentheses, done with exponents, no more multiplication and division. So now I'm going to add or subtract from left to right. I have negative 216 minus 2. They both are negative. It looks like I can join them up to make a negative 218. Okay. So let's try number 2. I see parentheses and I see a fraction. So remember that automatically makes those invisible parentheses. So let's do a little plugging and chugging here. 7 in for x, I'm plugging in a 9 minus 3. 2 and right beside that is x, or I plug in now 9 minus 16. Now recall the order now says that my whole numerator is in those invisible parentheses, and I need to simplify it down to one value if possible. My denominator is also in those invisible parentheses that I need to get down to one number as well. So on top, I'm going to start in the innermost parentheses, which is the 9 minus 3. So I get 7 in parentheses 6. And on the bottom, 2 times 9 is 18 minus my 16. Okay. Once again, though, I want that numerator to one value because it has those invisible, or now I made them visible parentheses. 7 times 6 is 42. On the bottom, I have invisible parentheses, or I can put them on there. 18 minus 16 is 2. And now, since one value is on the numerator, one value is in the denominator, I can actually finish this division or this fraction. But remember, that's really a division bar, 42 divided by 2, and my final answer is 21. Order of operations, be careful with it. Take it slowly, okay? I won't throw huge ones at you, but just remember what order you need to work in. All right, so quick review. We've done it a lot. Hopefully that makes sense. Okay. This next thing we're going to talk about is what we call set notation. We are going to use set notation. When needed, you need to write your answers in set notation, and I'll often remind you in the directions, leave something in set notation. So please be mindful of that, and please do your best to learn this, because this is probably something a little bit new and you didn't do a lot of it in Algebra 2. So a set is a collection of objects whose content can be clearly determined. Okay, so some things are in a pattern. Sometimes they're random. Sometimes they go on forever. Sometimes it's just a description. There's all kinds of ways to find a set. So one of them is this roster method, which you'll notice here, it's kind of a rule. I see 1, 2, 3, 4, 5, ... That means I have a pattern going here and all the numbers that fit that pattern. So it looks like it's just those whole numbers just going up by 1 each time. So I could continue 6, 7, 8, 9, 10. Obviously, I'm never going to get to the end of that set. We also have what we call a set builder notation, which tells us how we can build our set. And so in this one, it says X. It always starts with whatever the variable is, and then it does the bar, and it tells us the rule for what would make numbers in that set. So it just says X is a positive odd number. So I could start this, if I started to say what could be in there, it'd be like 1, 3, 5, 7, 9, and so on. But this is a set builder, which tells me how to do that, okay? When you're doing a set builder, you often don't list any of them. You just list the rule for them. Okay, so a couple things as we talk about sets. When I ask for set notation, that means I want your answer written with these nice fancy parentheses on both the left and right side. Okay, I understand they're not always easy to make. Mine are not beautiful, and I've been doing this for years. So do your best to give me those good squiggles, okay? So I know it's not a parenthesis. The other thing I want to set and make sure we know is if there's no value for inside the set, we have this little thing right here, which is called, and I'm going to spell this for you, the null set. Okay? Maybe you've heard of that before. Maybe you didn't realize it's spelled that way. But the null set means it's an empty set. There's nothing in it. Okay? Now, I do want you to be careful here. A null set is not necessarily a no solution. There are two different things here. The null set means there can be nothing that is agreeable to make a set. The no solution means that you're working with something else where there's no possible answer. So don't substitute one for the other because they're not always interchangeable, okay? The null set means there's an empty set when you're working in set notation. Okay, so a couple things here. On the left here, you're going to see these Venn diagrams so that they're trying to get you to see A is a set, B is a set. I don't even know what's in the set. It doesn't matter. It's just saying those are sets, okay? So there's some overlap of common elements, and there's some individuals on each side, okay? We have two kinds of things we're going to talk about with our sets right now. The first one is when we intersect our sets. And intersect, you'll notice by this symbol right here, this upside down U. So A, set A, when it intersects B. The key thing you need to remember about intersect is what does it share, okay? So these are the items that are shared between the two sets, the things that are in common, where they intersect, where they're in common. We also have, and you'll notice here they wrote it out in a nice way, right? X's where it's an element of A and of B, okay? It has to be in both of them. Then we have the union of sets, okay? And you'll notice on this one, this is the right side up U, okay, between that. And these is an element that is in one or the other. This one means all involved. So if it's in A, it's in the union. If it's in B, it's in the union. They don't have to have anything in common, okay? So you need to remember, because if there's no notes on your next quiz or test, that the U or union means all of them. And the upside down U or intersection means only what they have in common, what they share. Okay, so let's do a few of these examples and make sure we understand here. So the first one gives us a set of 1, 2, 3, 5, 7, 11, and it has the upside down U with 6, 12, 18, and 24. So that's asking us, what do they share? What do they have in common between those two sets? Is there an element or elements that are both identical from both sets? Well, considering the set on the left happens to be, I was going to say, yeah, it looks like prime numbers going up there. And the set on the right looks like they're all even. I don't see any in common. So because of that, instead of having a set with nothing in it, I just write the null set. That's my empty set, okay? There's nothing I can put in my new set for both of them. All right. On number 4, going to the right, I see another upside down U, which means another intersection. What is the same? Is there anything shared or the same between A, E, I, O, U and P, R, E, C, A, L, C, U, L, U, S? It's written for me and I still can't hardly say it. Is there anything in common? So I do think I see some, so I'm going to start my set. It looks like both of them have an A, so I'm going to include that. Both of them have an E. I'm going to include that. They don't both have an I. They don't both have an O, but they do both have a U, so I'm going to include that one. All right, and I think that's all they share. So there's my shared set or my intersection between my two sets. Rule of thumb, do they have to be alphabetical in there? No, but it's not bad practice to keep them organized, okay? As we do numbers, it's a nice idea to have them going numerically from left to right, from smallest to largest, okay? And that way, too, it's easier for you to say, did I get everything that should be in there? So it organizes it for us. For number 5, I have find from set on the left, 1, 2, 3, 4, 5, in union with the set 2, 4, 6, 8, 10. The union is all involved. So it means everything I see between the two is going to be part of my answer. So when I started off, my smallest is 1, I see a 2, I see a 3. Both of them have a 4. I have a 5, I have a 6, I have an 8, I have a 10. So everything involved is part of my union. Okay. For my next one, I have a set of GREAT in union with the null set. So I have a set with those 5 elements in union with nothing, with an empty set. Well, if it's union, it's everything involved. So with the union, I'm just going to have GREAT, everything involved. And notice, because we were playing with the words here, they're not alphabetical, but we'll leave it, that's fine. So on a side note, I just want you to know that if you happen to have this problem, if it was GREAT, and it said in the intersection of the null set, what do they share in common? Your answer would have to be the null set, okay? So that's a completely separate problem. So just kind of keep in mind, union joins everything, but the intersection has to be what they share. And if they don't share things, it's always going to have an answer of the null set. Okay, set notation. Be prepared to write some answers in that format, okay? All right, page 2. It's just going to get more fun from here, right? All right. I don't know how many times in your life you've done these charts. You've talked about all the different types of numbers that are involved in math, but again, it's a quick review. So this chart is actually one of the ways I like to view it, because I like to think of these are sets of numbers, and some of them are more specific than others. So if you think about it, and I like to kind of start in the inside, the most specific set of numbers I have, these are the natural numbers. And natural is kind of the key word here. These are what we find in nature, okay? Maybe known as the counting numbers. So if you think about when you find things in nature, now this is going to seem silly, but if there were nothing of something in nature, we don't even know it exists. Which means if it appears in nature, it has to start out with the number 1. We can't count 0 of something that we don't know exists, so we have to start with 1. So my natural numbers are like 1, 2, 3, and so on, right? We're not going to count 1 and 1.275 and 1.732. We're not going to count that way. When we see something in nature, there's either 1 tree, 2 trees, 3 trees, or there's just 1 tree. You can't have 1.65 trees, okay? So keep that in mind. Natural numbers are counting numbers, what we see in nature. You're going to notice this little symbol right here. It looks like an N with that double line on the crossing one. I'm not super concerned about these. I'm going to be honest. I forget what they are. I don't use them a lot. You may find someday in a college class or something, if you're talking, that they may use these. But if so, you're going to want to pull out these chart and review them, okay? I'm not going to use them. I'm not going to require you to memorize each of these numbers or each of these symbols for that. But that is the symbol for a natural number. Okay, so natural numbers are the smallest group of numbers that exists. The next set up with a little bit more to that set is the whole numbers. Okay, I say a little bit more to the set. There is one additional number in the whole numbers that does not exist in the natural numbers. And that would be 0, 1, 2, 3, and so on. So the only difference between a natural number and a whole number is that number 0. Everything else matches in those two sets. If I ask you for the intersection of the whole number and the natural number, you would tell me 1, 2, 3, and so on. If I said for the union, all you'd have to do is add the 0, okay? And by the way, those would be a roster list because we obviously aren't going to write every whole number down. Okay, our next group up with some more numbers involved, and by the way, those whole numbers use that funny looking W. The next group up are integers, okay? Integers involve the negative and positive whole, for lack of a better number, whole numbers, okay? The negative and positives. So now we can use also the negatives on this list. So we came from somewhere and we start out like -3, -2, -1, 0, 1, 2, 3, and so on, okay? Again, we keep those digits are hold that. We don't have any fractions or decimals yet, and we include the negatives and positive when we talk about integers. And it's symbolized by that funny-looking Z, okay? Next group up, the rational numbers, and you see that funny-looking Q there, okay? Now, rational. The best way to give you a definition, and this is something that if you always think about how this is given, you can always check to see if something is a rational number. The best definition for a rational number is a number that can be written as a fraction. Okay? Now, but it's like, wait, it only is fractions? No. If you think about all these numbers we've already talked about, can I write -2 as a fraction? Sure. Put it over 1, and it's now a fraction. So all these numbers beneath that we've talked about, they're all rational numbers. Obviously, a fraction, 7 over 4 over, 12 or something like that, that's a fraction, obviously, because it can be rewritten as a fraction. But don't forget, decimals can usually be written as fractions. And these would be decimals that end or repeat. Okay, so anything with a pattern on it or anything like that, those type of decimals could be converted over into a fraction, okay? And we'll do some math along the way with different options and different methods that will turn a repeating decimal into a fraction, okay? So that rational number list starts getting really big because we can write down all kinds of numbers there. Okay. You'll notice now that we have a line, and on the other side of this is irrational numbers. Okay? With the line, it tells us that everything on the left side does not go into the same set as these irrational numbers. They're completely different. They're not shared. There's nothing similar between them. So our irrational numbers are decimals that never end and never repeat. Okay? So when you think about things like that, an example of that would be pi, okay? We have that value that goes on and on forever. There's no pattern to it. It doesn't end. People are still trying to solve for the, I don't know how many digits of pi. Another group that you have to think of is something like radical 7, okay? A lot of our radicals that aren't perfect, they don't end. They don't have a pretty decimal to them. So remember, the most exact way to write them is as a radical 7, radical, and not get the decimal because we'd have to round it at some point to write it down. Another one that we will see sometime, and I think you looked at it in Algebra 2, is like the value e, okay? So there are some, and you just have to ask yourself, is it a decimal that I could put into a fraction, or is it something that's just strange, okay, and that I'm never going to be able to find the ending number? All right, all of these numbers, and by the way, that was that little I up there, the double I there. All of these are what fall into the category of real numbers, okay? So these are all real numbers. And by the way, this one is symbolized by this curse, the R with the double line, which we do use quite often. And I think you may have used in Algebra 2 if you ever had to find domain and ranges, and maybe you said, well, it's all real numbers. So that would fall in that number. All of these are all real numbers. What's the opposite of an all real number? Because is there another set? Yeah, there is. If I drew a line right here, I would tell you that what's over here are the complex numbers. What's a complex number? Anything that uses the imaginary I, okay? So we get into a whole new realm over there with complex numbers, new rules and all of this. For the most part, in algebra, we stuck to that real number R, but that complex did sneak in there. We're going to see both of them. We're going to graph both of them. We're going to work in both worlds, complex and real number R. So it's important to kind of know those differences, okay? So right now, just keep on thinking. The closer I get down to those natural numbers, the smaller the group is, and the more I go out, the larger it is. Now, every integer is not a whole number, but every whole number is an integer. So that when you're inside, everything around it going out is part of that set. But when you're on the outside, you can only go in as far as your rule applies. Okay? So let's go ahead and try example 7. And I will tell you on example 7, I do want to see these in set notation. Okay? So for 7, it says, list all the numbers from this given set above that are natural numbers. So I'm looking at my list up here. By the way, let's go through and talk about the list before we do all this. Negative 12, negative value, no decimal, looks good. Negative 2.3 with the bar above it. That means it's repeating. That means there's a pattern to it. So even though it's not in a fraction form, we could turn that into a fraction form. Some of you might know that 0.3 repeating is the same as 1/3. So technically this is negative 2 1/3, also known as 7/3, negative 7/3. So definitely we can write that as a fraction. All right, we have the value 0, 4/5, square root of 5. Is that a good radical? Is that a clean, pretty number? No, we're going to leave it. We have to keep in mind, what does that mean as a decimal? I see pi, 12.8, square root of 196. Now stop and remember, the square root of 196, that's a pretty number. The square root of 196 is 14. So if you keep that in mind, even though it's written with a radical, if it simplifies first, it doesn't necessarily have to stay a radical. Okay, I will tell you when you go through these, please, when you write your set, write it in the form they gave it to us at, but keep in mind in the back of your mind what its value actually is. So when I look at all those numbers, how many natural numbers are up there? Well, remember, natural are what we can count in nature. So I'm not even going to start at the negatives. I see some fractions and such like that. I don't want any of those. Do I have any natural numbers? I have 1, the square root of 196, because its value is 14. It has to be positive, has to be a whole number to be a natural number. All right, so I go to B and it says the whole numbers. So can I add anything to this natural number list and make it a whole number? Well, yep, it looks like I had a 0. So I'm just going to have 0 and the square root of 196. Integers. Back in that same list, are there things I can add? And again, since integers is the next step up, I'm just adding to that list I just found for whole numbers. So I can now include my negatives. Negative 12 is an integer. It's whole. Negative 2.3 doesn't work. 0, yep, that works. 4/5, no. Square root of 5, no. Pi, no. 12.8, no. But I can get the square root of 196 again. All right, next step up, rational numbers. Could I write it as a fraction? So I start at the left. Could I write negative 12 as a fraction? Definitely. Negative 2.3 repeating, we did already. And again, you don't have to know what it turns into, just if we could do that. Obviously the 0. 4/5 is a fraction. Square root of 5, no, that won't work. Pi, no. 12.8 could be turned into a fraction. 8 is like, what, 4/5 if we wanted to do that. So yep, 12.8 will work. And then, of course, the square root of 196 again will work. So we get a much longer list once we go to rational numbers. Irrational numbers, which ones in that set cannot be written as a fraction? Well, obviously everything that's rational cannot be in my irrational numbers. So there's 2 up there. The square root of 5 cannot be written as a fraction. It's going to be a decimal that doesn't have a good pattern and never ends. And pi. And then it says, which ones up there are real numbers? Well, to be honest, that's all of them. I don't see any i's in there. Since I don't see an I in there anywhere, I have the whole list. So I have negative 12, negative 2.3 repeating. Wow. I'm trying to fix my writing here. 0, 4/5, square root of 5, pi, 12.8, and the square root of 196. All right, do your best to kind of realize what's what here. It's not the end of the world, and you're going to be able to do fine in pre-calc not memorizing this chart, but it is good to keep in mind so we kind of know what we're looking at for answers, okay? All right, so let's come talk about some absolute value here. Absolute value is something we've seen for years as well, and we're trying to remember that the definition of absolute value is the distance from 0 to a real number, okay? And if we think about distance, distance will always be positive, okay, or non-negative. So if I think about it, these bars around this -5 is asking you how far is -5 from 0? Well, it's going to be 5 units away, so that's my answer, okay? So if I have something and I want to do the operation first, remember we said this earlier, these are like invisible parentheses. You have to get that down to a value inside first before you take the absolute value. So if I have 8 minus 12, I'm going to subtract that and get -4. Then I take the absolute value, and I'm asking myself, how far is it -4 from 0? And that would be 4 away from 0. Okay? So what absolute value bars does is say, how far are we from 0? Okay, notice on number 8 here for our first example, I'm evaluating or rewriting the expression without absolute value bars. Okay, so in a quick thought, and I'm going to use that 8 minus 12 we used earlier. Okay, so 8 minus 12. Well, if I just do the math, I get -4. Okay, I don't want the answer of -4 because it is negative. If I would have split this around and said 12 minus 8, I get my answer of 4, which is the same thing as the absolute value of -4. Okay, so when it says evaluate it, that means if I can simplify it, I do, or rewrite it so that we could have the same answer without the absolute value bars. So this would need the absolute value bars to get the 4. This is the same problem rewritten with the same answer without the absolute value bars. Now, I'm telling you that because in this first one, square root of 7 minus 10 and the absolute value of that. Now, I'm going to tell you right now, square root of 7 is irrational. I can't just turn that into a decimal or round it and get an answer. So if I want the same answer for this without absolute value bars, I have to think of what's happening here. Square root of 7. Well, the square root of 4 is 2. The square root of 9 is 3. And this falls somewhere between 4 and 9. So that means this square root of 7 is 2 point something, something, something. I'm not sure, but it's there. So if I think if I have 2 point something minus 10, I'm going to get a negative value. That's not the same as the absolute value. So if I want to rewrite this in an equal or equivalent without the absolute value bars, what I do is I just flip it and I write it 10 minus the square root of 7. Just like I did over here when I just flipped it and said, well, 12 minus 8 is 4, which is the same as the absolute value of 8 minus 12. So if you can't actually find the exact value, simply make sure the bigger value is in front, subtracting the smaller value, and it'll give you the same equivalency as what the absolute value bars would. I hope that made sense. All right, number 8. The absolute value of the absolute value of -5 minus the absolute value of -12. Remember, absolute value bars really are treated like parentheses. Start in the innermost and work out. So in the inside absolute values, I have the absolute value of -5, which is asking me how far is -5 from 0? Well, that's 5. Minus, how far is -12 from 0? And that would be 12. Now, those were the inside absolute value bars. I still have the outside ones. So now I have 5 minus 12. Because these are values that I can actually comprehend, they're not rounded, they are rational, I can go ahead and continue the math. 5 minus 12 is -7, and the absolute value of -7, or how far is -7 from 0, is just 7. Okay? So if you have something that's irrational, like the square root of 7, you always want the biggest number first, and then just rewrite it without the absolute value bars. But if you can actually do the math, do the math. Okay, so the distance between 2 points on the real number line. It says if you have 2 points on a real number line to find its distance, just subtract them. And notice I can subtract them in either order. And I should, if I use the absolute value signs, get the same value. So it says find the distance between 9 and -12.4 using absolute value. So if you think about this and just a visual on your number line, right? So you have the 0 here. Negative 12.4 is over here somewhere, and 9 is over here. It's asking us how far between these two values. I have negative 12.4 to 0, then 0 to 9, and I'm working on this. But what they're saying is what you should always be able to do is do an absolute value of 9 minus the second number. Okay, the first number minus the second number, and the absolute value. 9 minus a negative 12.4 is the same as add the opposite, and I get 21.4. Okay? And it's positive, so I get 21.4. Just a note, if I had flipped them around, and I put negative 12.4 minus 9, because they're both subtraction in there, or both negatives, I join them together, I get negative 21.4, but I still take the absolute value, which is 21.4. Okay, so when you're finding the distance between 2 points, you simply subtract them, and you take the absolute value because you're finding the space between them, how far they are apart from each other, basically, and that's why we subtract them. Just a heads up, and for those of you that love geometry, if you think about the distance formula, how far between 2 points, we subtracted between the x values, we subtracted between the y values. And that comes from this same concept as subtract the difference between the points. Obviously there, things were on a slant, so we had a little bit of difference, okay? But just kind of a connection there about the subtraction. All right, moving on. Page 3 is no new examples. It's simply going through some of our properties that, again, we've seen over the years, and the question is, do we remember them? I'll throw these properties out often and just kind of remind you of them, but it's something just to keep in mind. There gets to be a point, the higher up you go in math, that the fewer and fewer numbers you will see. And you have to remember what are properties that hold true that allow me to simplify or combine or something like this with values or non-values, like just variables, okay? So we're going to start with the first property. And again, I'm asking you to try your best to try to keep these straight, but we'll kind of go from there and figure out if you can keep them straight. So my first two up here are the commutative property of addition, commutative property of multiplication. Obviously, the addition and multiplication makes sense. Sometimes you're adding them and sometimes you're multiplying them. How do you remember when a problem has the commutative property? Okay? The way I remember it in my mind is commutative reminds me of the word communicate, okay? So if you think about communicate, when I communicate with someone, we talk back and forth. I talk, you talk, I talk. The order in which we talk does not matter. Our communication goes back and forth in any order, okay? So the important thing is here we can go in any order. And if you've heard me say it before or heard anybody say it, I can say 13 plus 7 and join them together, or I can add 7 plus 13. It doesn't matter which number comes first. I simply need to add them in one order or the other. The same with multiplying. I can take 6 times 5 or 5 times 6. I just need to do the multiplication. So if I can switch the order in which I write it, it's fine. Now, quick side note, I can't have a commutative property of subtraction. I can't say that 7 minus 2 is the same thing as 2 minus 7. They're not. That's why you don't see a commutative property of subtraction. We also cannot divide in any order. You have to divide in the order they give you. So you only can have commutative property in addition and multiplication. All right, so my next one here is going to be the associative property, okay? So the associative property of, once again, just addition and multiplication, okay? There's only those two have the associative property. So when I'm trying to think about this associative property, what does it mean? I associate, okay? If you think about it, I associate with new friends, okay? Or old friends, it really doesn't matter. And what the associative property does is it changes my grouping, okay? And again, I can only do this with addition and subtraction. So in my first example, 3 was playing by themselves and 8 and X were being friends together. But then they said, well, I'm changing it up. 3 is going to play with 8 and X is going to hang out by himself. So when you think about it in addition, it really means I can add those 3 and 8 together. but it depends where my parentheses are here. But I'm allowed to group to new friends and still have the exact same value. The same thing with multiplication. 3 and x were hanging out together while negative 2 was by itself, but I could put the negative 2 and 3 together in their same grouping and have x hang out by himself. So that's where I kind of associate with new friends is a grouping. I'm looking for parentheses. I'm looking for things differently to be put together when I associative, okay? Next one is the distributive property. Again, this one I feel sometimes is self-explanatory. If I have a value on the outside of my parenthesis, it distributes to every term inside. And remember, terms are separated by addition or subtraction. So if two things are multiplied in there together, that outside value only goes in once because terms can only be separated by an addition and subtraction, okay? All right, moving on to the identity property. And again, you'll notice I try to find you little ways to remind your brain, how can I remember this? So my identity property of addition, my identity property of multiplication. Your identity, okay, is yourself. Who are you? Who do you need to stay? Okay, so you want to stay yourself when your identity. So that means if I have a value and I want to stay myself, the only thing I can add to it is 0. If I have myself and I want to stay myself, the only thing I can multiply by is 1. So identity property of addition is when I add something 0 to something. And the identity property of multiplication is when I multiply something times 1 and it keeps itself. So you always want to equal yourself with the identity property. And to be honest, I think it sometimes gets mixed up to here with the inverse property, probably because they both start with i's. But with the inverse property, I want to undo, okay, to go back to the base. So with this, I'm undoing whatever I had, and I go back to the base, okay? So if I had a square root of 5, I'm going to do its opposite or its inverse, so subtract or add the negative opposite square root of 5, and I go back to 0. If I had negative pi, I add pi, and I go back to 0. Notice on all of these, I'm doing the opposite operation to go back to the base or 0. For the inverse property of multiplication, I multiply by its reciprocal, okay? Or I kind of do the division. So I have 7, I multiply by square root of 7, 1 over 7, that's a fraction, and I go back to this base, which is 1. Now, you'll notice on this one, when I have 1 over x minus 3 times x minus 3 equals 1, again, this division and the multiplication cancel each other, and I end up with the 1 back there, okay? So inverse undoes things, undoes an operation to go back to the base, which is 0 or 1. Identity, you keep the same answer you started with, and that means you added 0 or you multiplied by 1. Okay. Those are our big properties. That's what we want to know. Let's practice a few more to end these notes. All right. So on 11 and 12, I'm saying state the property you see illustrated. And please be specific as far as addition, multiplication, or as specific as the property allows you to go. So the first one in 11, I see in parentheses 2 plus 3 plus the parentheses 4 plus 5. Equals in parentheses 4 plus 5 plus parentheses 2 plus 3. Now, if we were doing these in person, I'm hoping, and I probably, good chance is I may have tricked somebody. So if you're thinking in your head right now, that's associative, they just made new friends, be careful. I tried to trick you here. Definitely parentheses, but just because you see parentheses does not mean I'm associating with new friends. If you peek carefully, 2 and 3 are still hanging out with 2 and 3. 4 and 5 are still hanging out with 4 and 5. No one made new friends. So it's not associative. However, notice that 2 and 3 used to be in the front and 4 and 5 in the back. Now 4 and 5 are in the front, 2 and 3 are in the back. So it's not new friends that happen. It's a new order in which they're doing things, and a new order means that we have the commutative property And once again, I told you that please try to be as specific as possible. And it looks like this whole thing we are adding. So it's going to be the commutative property of addition. All right, second one. 1 over x plus 3 times parenthesis x plus 3 equals 1. Well, once again, if you think about it, because these two things will cancel and you are equal to 1, that is the inverse property. Inverse is what wants things to cancel. And it looks like we have the inverse property of multiplication since we are trying to get rid of things by multiplying. Okay, quick side note. Why did they bother to tell us x cannot equal negative 3? What does that have to do with anything here? And I will warn you, this is something we have to be a little bit more careful with, notice, and try to make sure we state when we're working here in pre-calculus. If x was negative 3, and I plug it in down here, negative 3 plus 3 would give me a 0. Are we ever allowed to have a 0 in the denominator? No. That's not allowed, so that's why they give us that qualifier, like we can do this problem and we can get Z1 as long as we never use the value negative 3. Every other x will work, okay, but not negative 3. So side note on that, not something that deals with the properties as much as always remember, never let the denominator equal 0. All right, a little bit trickier simplification here, just to keep sure we can go through and do variables along with our order of operation. So I think about, please excuse my dear Aunt Sally here, and it looks like I have parentheses in parentheses. So I'm going to start in the inside here. I'm going to leave 18x squared plus 4 the same, minus. And in this parentheses, I'm going to distribute inside here. So I have x squared minus 2, by the way, can't do anything, so I can distribute or use my distribution property. 6 times x squared, 6x squared. 6 times negative 2, negative 12, plus 5. Now I notice that inside my brackets there, I can do some more simplification since I got rid of the first set of parentheses. These two are both integers, so I can join those together. So I'm going to leave 18x squared plus 4 minus, I'm not touching that 6x squared right now, but my negative 12 plus 5 will make a negative 7. And I'm ready to go now. Now, be really careful with these brackets. I would like to get rid of them. Are they needed? And the answer here is yes, because outside here is this negative, and then it's the brackets. Don't forget this negative is really in front of this invisible 1, which means I have a negative 1 out front, and that needs to distribute in. So I'm going to end up with 18x squared plus 4. Negative 1 times 6x squared is negative 6x squared. Negative 1 times negative 7 is positive 7. Now I don't have brackets. I don't have parentheses. I can continue. My parentheses are done. Exponents, I have some, but they are not able to do anything because they're on a variable. So I'm just going to leave them. So I look for multiplication and division. Nothing I can simplify. It's time to add or subtract from left to right. Like terms, 18x squared minus 6x squared leaves me with 12x squared. Positive 4 plus 7 makes positive 11. And I've simplified this as much as can be simplified. So again, evaluate or simplify means I've just simplified as far as I can. I can't solve it because I don't have an equal sign. All right, 14, a lot's going on here. Fractions, don't forget, I need that top, the numerator down to 1 value and that denominator down to 1 value. So up on top, I'm going to do two things here at once. 5 times 2 is 10. 3 squared is 9. That looks cleaner already. Down here at the bottom, I have parentheses and parentheses I need to take care of. I'm going to go ahead and say that 3 squared is 9. Minus a negative. Remember, keep, change, change. So that's going to become a plus 2 and a squared. Okay. 10 minus 9 on top. 9 plus 2 inside that parentheses makes 11 and squared. I'm going to go ahead on the top, 10 minus 1, get it down to 1. 10 minus 9, my tongue's ahead of my brain or something there. 10 minus 9 is 1, and 11 squared is 121. Can I do anything more with this fraction? The answer would be no. I think I'm good at 1 over 121. All right, are we on our last one? Example, write this phrase as an algebraic expression and then simplify the expression. Let x represent the number. Okay, so using some of our algebra terms that we know, our vocab, turning them into an algebraic terms into number sentences, okay? The difference, remember difference is when we subtract, between 10 times a number, so we know that number needs to be x, so 10x, and, so remember, this is the first thing that's subtracting, and 6 less than 4 times the number, okay? Less than, more than, what that does is basically tell us we're going to flip these two things. If it's just less, it's just subtract. Less than means flip them while you subtract. So less than is still subtraction, but 4 times the number is 4x, and it's 6 less than that, so that's going to flip that to the back. So notice I really need those parentheses. And it was the difference between this 10 times the number and the 6 less than 4 times the number. So I have a subtraction right in there, okay? That's my phrase as an algebraic expression. Now I need to simplify this, okay? So now this is one part of my answer, right? I'm going to distribute. Remember, this is just like that earlier example, and this negative is actually holding a invisible 1 behind it, right? So when you have that, make sure you distribute it to both. So really I have 10x minus 4x. Negative 1 times negative 6 is positive 6. Now I can join like terms, and I get 6x plus 6. So my original expression is here. My simplified expression is here. Okay? I'm going to be honest. This feels like we had multiple lessons here. Little ones, a lot of randomness maybe. It doesn't all seem to gel together. But again, that's what this prerequisite section is going to be. A lot of little things to remind you that, do you remember how to do this? So if you like to practice, page 15 to 17 has some great values. I like to tell you 3 through 126 by 3s, but I'm going to be honest. If you want to check your answers, you can just do the odds, because then you can check all the odd answers in the back of the book and see if you're on track. Another option, and I know I told some of you, I forgot to tell some of you, Slater.com's your friend. You can go check your work on Slater.com, because I'm not grading this homework. I just want you to understand what you're doing, okay? So go ahead and practice as much as you need or as little as you need, and just know that I'm holding you responsible for this material. Good luck. Let me know if you have any questions.